Right, what I want to talk about here is atomic models, and primarily Rutherford's model. But let's just have a quick look at Thomson's model. This is the one you'll hear as the plum pudding, and it's called that because it visualizes the atom as like this circular spherical object with plum bits in it or raisins or something like that. But what they actually were electrons. Thomson had discovered the electrons in the 1890s, I think. They were called some sort of rays. They thought about them as rays back then, but Thomson ended up figuring out that they were electrons. A guy called Millikan figured out the charge. So his idea was that these negative electrons were in this sea of positive pudding, and that the electrons were the negatives. There was another guy before that, Dalton. Dalton he had the idea that the atoms were just these hard units, little spherical balls, and that would be like an iron spherical atom, and that there'd be calcium spherical atom. So Thomson, compared to Dalton, was definitely an improvement. He had discovered the electron. He knew there must be positive charge because the electrons were neutral. But Rutherford, the great New Zealand physicist, and really he was great, supported this Thomson model. So he did some experiments. Radioactivity had been discovered at this stage. You probably all heard about Madame Curie. And the particle that Rutherford used was called an alpha particle, which is a helium nucleus. So it's got no electrons, so it's 2 plus charge, plus 2 charge, 4 mass units, which are protons and neutrons. So 2 atomic number means it's actually helium. So it's 2 protons and 2 neutrons together, and no electrons. So it's charged. Charged was important, light was important. The experiment they were going to do was to shoot this through very thin gold. Why gold? Because gold could be hammered out to very, very, very thin sheets. And alpha particles are stopped by about 5 centimeters of air. Will stop alpha, or a thin sheet of paper. Thin sheet of paper. So to get the alpha particle and use it as a missile to fire through gold atoms, you need a really, really thin sheet. And so Rutherford's idea was, if we can use these little alpha particles as missiles and shoot them through the atoms, what the atoms do on the other side here is going to tell us about the structure in here. Of course, he was thinking that the old Thomson model was correct, and that there was all this positive charge with these little electrons inside. And so he was expecting some very, very weak deflection. And he was going to use a screen over here, sulfide screen, zinc sulfide screen. And the reason he used that was because when the alpha particle ended up hitting over here, there was a brief flash of light. So they did this in the dark, so that they could see. And his assistants, Geiger and Mueller, would stay up all night doing thousands and thousands of these, observing where the flashes were. And Rutherford worked out this fairly complicated equation that showed what the deflection should be if the Thomson model was correct. He expected very, very weak deflection. Now the point was, mainly he got no deflection. So this already was going, okay, the model's not looking too good. Because he expected a small amount. So that led him to believe that the atom was mainly empty space. There wasn't this weak positive charge all over the place. It wasn't there. Otherwise you get a slightly bit more deflection. He did his whole experiment in a vacuum, because obviously if there was air, the air could block the alpha particle, or the air could interfere with the trajectory And if the air interferes with the trajectory, then you get a little bit of deflection and you go, wow, yeah, the atom's like this. But it's not. It's got nothing to do with the atoms. It's just the air affecting it, right? So, but what he did find was sometimes there was a bigger deflection over here. Much more than there should have been with this positive. So it led him to believe that some slightly larger deflections led him to believe that their positive charge must be concentrated. Concentrated positive charge. But then there was these extreme deflections where the electrons, or not the electron, the alpha particle bounced back. This was impossible. This meant that the positive charge must be really concentrated and that you'd scored a direct hit. That was about 1 in 8,000. Now, if 1 in 8,000 recoiled like this, then, and that was only if all the gold atoms' positive charge was in this really tiny space, that was showing him the nucleus, which was 20,000 times smaller than the diameter of, or the radius of the nucleus is 20,000 times smaller than the radius of the atom. That Rutherford was able to deduce that from the fact that to get an alpha particle traveling at 5% the speed of light to recoil, we needed to put all the positive charge of the nucleus of the gold in that smaller space. So the recoil told him how big the nucleus was. The deflections told him, and that was where an alpha particle came close to the nucleus, told him that the positive charge was very concentrated. He hadn't scored a direct hit yet there, so he couldn't really figure out the size. And the lack of deflection in nearly all the alpha particles going through told him that it was mainly empty space. So understanding this Rutherford experiment is very important in level 2 atomic and nuclear. Hopefully we've covered the main points there.